Noir Plasma Chrome Bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.
This website makes learning so easy. I found all my resources here.
Like what you share.
Welcome to This Explainer. Today, we're diving deep into the world of advanced linear programming. You know, you might not see it, but there is a hidden mathematical engine basically running our world right now. It routes global supply chains, allocates your internet bandwidth, and manages massive portfolio risks. It's an absolutely incredible field of optimization, and today, we're going to figure out how it all actually works.
Here's our roadmap for today. We're going to cover 1. Foundations of linear programming, 2. Polyhedral geometry and extremes, 3. Duality and complementary slackness, 4. Classical solution paradigms, 5. Modern interior point methods, and finally, 6. Integer unknowns and unimodularity.
All right, let's kick things off with Section 1, Foundations of Linear Programming. So, diving right into the foundations, it turns out that every single linear programming model is built on just 4 core elements. First up, we've got decision variables. These are just the unknowns we're trying to figure out, like, say, exactly how many delivery trucks to send to a specific warehouse. Second is the objective function, which is our ultimate goal, right? Maximizing profit, minimizing costs, that sort of thing. Third are linear constraints. These represent our real-world limits, like the maximum capacity of a factory. And fourth, non-negativity restrictions, because, well, obviously, you can't allocate a negative number of physical trucks. It just doesn't make sense. But here's a kind of fascinating quirk. You can't always just throw these raw inequalities into an algorithm and expect it to spit out an answer. Nope, we actually have to translate them into standard matrix expressions first. For example, we use something called the augmented or slack form. This means we're literally adding slack variables to turn fuzzy inequalities into exact equals. Basically, we're giving our algorithms a highly precise mathematical map so they can find the exact geometric corners we want to target. Which brings us perfectly to Section 2, Polyhedral Geometry and Extremes. Now, if we take all those algebraic constraints we just talked about and actually graph them out, the space of all allowable legal choices forms this multifaceted 3D shape called a convex polyhedron. Think of it like a really sharply cut diamond. This physical space is bounded by its outer faces, and those faces intersect at extreme points, which are essentially the corners or vertices of the shape. And this is exactly why linear programming is solvable in the first place. The fundamental theorem proves that if there is an optimal solution, it's always going to occur at one of these extreme corner points. In fact, thanks to the Minkowski-Weil decomposition theorem, we know we never actually need to search that vast continuous volume inside the shape. We literally just have to check the corners on the outside to find our absolute best answer. Moving right along to Section 3, Duality and Complementary Slackness. Okay, this absolutely blew my mind when I first learned it. Every primal optimization problem we create, like maximizing factory output, has a hidden, perfectly symmetric dual problem mirroring it. It's like a mathematical mirror world. This dual problem completely flips the perspective, usually calculating the exact minimum cost of the resources being used. And the strong duality theorem proves something pretty incredible. If you find the optimal solution for one, you've automatically found it for the other. Their optimal values will be exactly equal, no way around it. So that begs the question, how do we know for absolutely sure when we've hit that perfect solution? Well, the complementary slackness theorem gives us the answer. It basically proves that we achieve true optimality only when the math of our primal problem and that dual mirror world perfectly align. To put it simply, you hit the jackpot when the duality gap between these two worlds completely closes to zero. Let's look at how we actually get there in Section 4, Classical Solution Paradigms. So how do we systematically find that perfect corner point we were talking about earlier? Enter George Danzig's famous 1947 simplex method. Instead of just blindly guessing, simplex essentially walks along the outside fences, the outer edges of our geometric shape. It checks a corner, looks for an adjacent edge that improves our goal, walks to that next corner, and just repeats this loop until it reaches a peak where literally no better path exists.
But, there are other ways to navigate. Take the crisscross algorithm. It totally ignores the standard rules. While simplex absolutely needs a valid starting point, crisscross can start from literally anywhere, even a completely invalid impossible point. It ignores the real number magnitudes and just relies on combinatorial positive and negative signs to essentially crisscross its way through both the inside and outside of the shape until it zeroes right in on the optimum. While simplex is incredibly practical, it does have a massive catch. On specially constructed, highly complex shapes, like the famous Clementi hypercubes, the algorithm can actually get tricked into checking almost every single corner. That takes an exponentially massive amount of time. And this terrifying worst-case reality, that is exactly what drove mathematicians to scramble for completely new, much faster methods to handle modern, global-scale industrial problems. This leads us straight into Section 5, Modern Interior Point Methods. That exponential time problem actually sparked a 40-year arms race to guarantee faster, polynomial time solutions. Starting back in 1979, Cauchyn's ellipsoid algorithm proved these problems could be solved efficiently in theory. Then, by 1984, Karmakar's projective scaling methods actually started beating simplex in practice. And this speed just kept compounding, all the way up to 2020, where researchers like Brand proved we can now solve these massive linear programs almost as fast as a computer can do basic matrix multiplication. I mean, that is blisteringly fast. When you compare them side by side, the difference is really striking. While simplex walks the outside edges of our shape, interior point methods use mathematical logarithmic barriers to basically carve a smooth, continuous tunnel straight through the interior to reach the optimal corner. So you might be wondering, why do we still even use simplex? Well, a concept called smoothed analysis shows that on normal, everyday, sparse problems, simplex is actually highly efficient. But for massive, dense industrial networks, tunneling through the center with interior point methods is absolutely the undisputed king. Up to now, our math has sort of just assumed we can divide things infinitely. But think about the real world for a second. You can't route half a delivery truck, right? You can't schedule a fraction of an airline pilot. This highly practical demand for whole numbers introduces a massive, and I mean massive, complication to our theoretical models. And that brings us to our final part, Section 6, Integer unknowns and unimodularity. You see, forcing our variables to be integers turns our model into an integer linear program, which is notoriously NP hard to solve. But researchers actually found a mathematical cheat code. The Hoffman-Kruskal theorem proves that if your constraint system uses what's called a totally unimodular matrix, which is really just a fancy way of saying its mathematical subgrids only ever evaluate to 0, 1, or -1, magic happens. You can just solve the easy fractional version of the problem, and the math guarantees that your optimal corner point will automatically be a perfect whole number. Literally no rounding required. And this concept expands even further with something called total dual integrality, or TDI. Basically, researchers proved that every single whole number shape we want to navigate can be defined by this perfectly structured math. And guys, this isn't just abstract theory. This structural guarantee forms the exact mathematical backbone for the combinatorial optimization running our world today, from shortest path GPS routing to mapping massive global network flows. When we take a step back and synthesize all of these methodologies together, you can really see a brilliant evolution. I mean, we started decades ago just walking the outside edges with Danzig's pivot rules. Then we learned how to tunnel straight through the center. We implemented randomized linear algebra. And we uncovered these deep structural bridges that let us flawlessly solve discrete, real-world integer problems. It's honestly a stunning arc of human progress. Linear programming truly is this incredible engine of mathematical efficiency. From the basic simplex method in 1947 to modern algorithms operating at the blistering speed of matrix multiplication, the evolution has just been relentless, which leaves us with a pretty big question. With algorithms this fast and frameworks this structurally sound, what new, massive global complexities will linear programming conquer tomorrow?
Keep optimizing, and I'll catch you in the next explainer.
Like what you shared.
This website makes learning so easy. I found all my resources here.
Noir plasma chrome bleed. Unlocking knowledge, inspiring innovation, empowering curious mind.